Hello, everyone. This is the power of pi, and today we're going to be looking at a very nice AIME problem, the 2006 AIME II Problem 10, which features a pretty nice combinatorial identity, and it's a problem we can learn a lot from. So, 2006 AIME II. So without further ado, let's get into it. So 7 teams play a soccer tournament in which each team plays every other team exactly once. No ties occur. Each team has a 50% chance of winning each game it plays, and the outcomes of the games are independent. So this just seems like a regular, round robin tournament. Round robin is basically where each team plays the other exactly once, and they all have a fair shot. Okay. In each game, the winner is awarded a point, and the loser gets 0 points. The total points are accumulated to decide the rank of the teams. In the first game, in the first game of the tournament, Team A beats Team B. The probability that A finishes with more points than, okay, we want to find the probability that A finishes with more points than B. So what I'll do is I'll call these teams A, B, C, D, E, F, and G. So A plays B. So what other games will A play? A will play against C, D, E, F, G, and then no more, because each team exactly once. And then B, other than A, will play against C, D, E, F, and G. Okay, so now with this information, we're given that A has already won a game. So basically, in order for A to win this tournament, he needs to win at least as many games as B. So if B wins 3 games from C, D, E, F, G, A must win at least 3 games from C, D, E, F, G. In that way, A will have one more victory in the end than B. So our task is to compute the probability that they win at least the same number of times. So I'll write this as the probability that A win is at least B win. So this probability itself is a little bit hard to calculate, but through like some motivation, we can actually write this as P that A wins is greater than B win, for the reason that if A and B do not tie, since they have a 50% shot to win each game, A winning more than B is exactly a symmetric outcome as B winning more than A. So it's easier to write this as A win is greater than B win, and then adding this to probability that A win is equal to B win. And then I'll just call this the probability of a tie. So now let's basically set what I said in words and put it into like an equation. So the probability that A win is greater than B win is going to be 1, given that they don't tie. So probability that tie. So if they do not tie, there's going to be basically an equal chance that A wins more than B, and there's an equal chance that B wins more than A. So divide by 2. So that'll be this thing over here. And then probability that A win equals B win, that we call that probability tie. So our task is to now find probability 1 plus probability tie over 2, which actually does not seem too bad. If we go back over here, we want to find the probability that they tie. So probability both win, let's call it both win K games with 0K5. So what's the probability that they both win 0 games? In other words, they lose every game. Well, let's actually not calculate the probability for now. Let's calculate the number of outcomes, because probability is just number of outcomes over total outcomes. So let's calculate number of outcomes. So for them to win none of the games, we choose basically 0 games for them to win. How about the probability? How about the number of ways they win 1 game each? Well, we choose 1 of C, D, E, F, G when phi choose 1 ways, and similarly for B. And we do this until, say, A and B win all the games. That'd be phi choose phi times phi choose phi. So in other words, basically this thing, you can jump to this immediately. It's just K equals 0, the sum from K equals 0 to phi if phi choose K squared. So that's the total number of successful outcomes. How many are in total? Well, for each team, the outcome is either a win or a loss, each with a 50% chance. So, the outcome is win or loss. So 2 outcomes over 10 different games, C, D, E, F, G twice. So this. So this is what we want to calculate, and this is P tie. Now, obviously, calculating the sum by hand is not hard at all. But let's actually maybe like go into something a bit more interesting. I want to find the sum of summation from, I guess, k equals 0 to n of n choose k squared. I want to generalize this result because it's really cool. So how can I do this? Well, what I'm going to do is the task is now going to be, I'm going to consider maybe a set X with elements x1, x2, all the way until xk, and y, which is elements xk plus 1, all the way to x2k. So now what I want to do is I want to choose a set of k elements from x or y. So how am I going to do this? Well, firstly, I can choose all my elements from x. So k choose k, and consequently, I'll choose from the k elements of y, I'll choose 0 of them. Or I'm going to write this as this. So I can choose 0 elements from x, and then all of them for y. I can choose 1 from x, and then I can choose 1 for y. And then all the way until I can choose k minus 1 from x, and I can choose 1 from y, and I can choose all from y, and all from x and then 1 from y. So really, what is this sum? I'm going to utilize the fact that n choose k is n choose n minus k. Algebraically, that should be clear, and then combinatorically, I guess it's basically counting the same thing. One is counting choosing k objects from n, and the other is choosing the n minus k objects that will not be in our set. So that's clear, and then so this is just k choose 0, k choose 0. So applying the property to all these, plus k choose 1, k choose k minus 1, which is k choose 1, all the way until k choose k, and then k choose k minus 0, which is k choose k. And then this is precisely kind of what we want to find over here. So we've counted this in one way, but then there's another obvious way to count this. We have a total of 2k elements, 2k elements. And what essentially I'm doing is I'm choosing k elements from the 2k. I've done it basically by a casework approach where I choose how many I want from x and how many I want to choose for y. And then for now, I'm just going to say 2k, and then I want to choose k. So we've established this using what we count in double counting proof. So with that being said, when we wanted to calculate phi choose 0 squared plus phi choose 1 squared to phi choose phi squared, so this is actually just n choose 0 plus squared plus n choose 1 squared plus all the way to n choose n squared, which we've just established over here is 2n choose n. So 2 times phi choose phi is 10 choose phi. So probability of pi is the 10 choose phi over 2 power 10, which is what we've discussed over here. Okay, and then now this is just computation. 10 choose phi is this, 5 factorial, that goes 5, 4, 3, 2. And then boom, boom, boom. This is 2 squared times 7 times 9 over 210, which is 63 over 256. So 1 plus 63 over 256 over 2. Again, just recall that came from this part over here. So we're just going to utilize that. This is going to be equal to 319 over 512. So this is m over n. Problem that wanted us to find m plus n, so our answer is 831. So hopefully you guys enjoyed that kind of like that deep dive into this problem, as well as really a cool combinatorial identity we discovered. Make sure to subscribe, and I'll be posting a new video shortly.